So I'm going to talk to you today about new solutions for smart buildings, and I'll try to cover a spectrum of activities from early stage R&D through deployment. Before the technical details, I'm going to give you an introduction to me, some of my background, starting with education and then moving into career. So I came out of the public high school system from both Seattle as well as South Carolina, kind of split my time between the two locations. And I had a few really key and important introductions to STEM at that point in time. First was a teacher who got me directed into the MESA program, which is where I think I first heard the term engineering as like a professional career and a field of study. A big thing that I remember was an event hosted in the Seattle area at the time, and we're talking about like the early 1990s, where Bill Gates hosted an event, Blacks at Microsoft, and that brought together students from across the Seattle public high school system to go across the bridge over to Redmond, over to the campus there, and really start to understand what happened, what was happening at that company, and what folks were doing. That was a big standout for me. I was also, through the MESA program, connected with a mentor. That was also a new notion to me at the time. You know, what even was a mentor? Sadly, I probably didn't take as strong advantage as I could have. But this woman worked at Boeing and was an aerospace and mechanical engineer, and another strong connection point. So it was ingrained in my mind. Then when it was time to go to college, that, hey, engineering is something that I could pursue, and teachers said, oh, hey, you're good at math and science, so give it a try. So I went to Harvard University as an undergrad, majored in mechanical engineering, continued with mechanical engineering in graduate school at UC Berkeley. I started there master's only. And found that the research environment, the academic environment, was really something that resonated with me, that I was well suited for, that made me happy. So I continued on for a PhD and had a big topic change and shift in focus between master's and PhD. So that really lengthened my time as a graduate student, but that was fine. Career path. When I started as an undergrad, internships they really weren't as common as they are today. It was not the routine that, of course, you do that, especially as a STEM major. So the first thing I did was go right back home after semester end and continue the jobs that I had always worked, which was at Godfather's Pizza. I went back to the pizza joint. My first step up then was actually shifting to a job at the county unemployment office in King County. And that was actually a major step up, but it was boring. It was only filing, really, essentially. At the very end of my period as an undergraduate, I got connected with some engineers who were working around astronomical instrumentation. And that's when I finally picked up a job that had anything to do with technical anything whatsoever. We worked on instrumentation for the Apache Point Observatory in New Mexico in service of the Sloan Digital Sky Survey project, which was the largest scale survey of galaxies. At some point when I was getting the master's degree, I had a co-op position at NASA Goddard, that was in Greenbelt, Maryland, right outside of DC, continued working in instrumentation in support of astronomers and the work they were doing. So got to do like finite element analysis and modeling for instrumentation that was being sent up to the International Space Station. As I mentioned, I switched topics a lot throughout between master's and PhD. My PhD landed me in an area adjacent to building technologies, which is what I'm going to talk about today. Right out of graduate school, I started with a postdoctoral position at Berkeley Lab, and have remained there ever since. A little bit of grounding now. So I've been at Berkeley Lab for, I think it's 13 years now, and October is my anniversary month. So that's always fun to recognize. Throughout my time there, I've built up now a program in commercial building analytics and controls. The purpose or motivation of our group is to accelerate the adoption as well as the technical advancement of analytics, diagnostic, and advanced control solutions that are really powerful but underutilized in the commercial building stock. And we really work both sides of the spectrum, from new technology development and pushing new solutions to market, as well as engagement with technology vendors, building owners and operators, and utility programs to try to spark that market pull for those technologies that are commercially available. So it's really important that we maintain, as well as a building science grounded technical expertise, a strong hold on market intelligence to understand what's the state of currently available technology, what's under the hood, how is it best used, and how can we move the state of technology forward. So that's the backdrop of what I'm going to bring to you today in the primary technical presentation around smart buildings for the commercial technologies for the commercial sector. So as context, I think we could all recognize and appreciate that the data revolution is driving things in many, many fields. For us in buildings, it's really bringing about a surge in new solutions for both control as well as analytics. So we've got researchers and product developers all exploring in parallel, how can machine learning, how can Internet of Things, how can cloud computing transform the way that we operate our buildings? And what we really need to understand is, how are users benefiting from these new technologies? What are the as operated costs? And what are the outstanding development opportunities that are going to present the most potential to advance usability, scalability, and performance of the smarts that we're embedding into our buildings? So in today's talk, I'm going to cover a little bit of the state of the art. I'm going to talk about a recently concluded study and results to document those as installed costs, savings, and best practice uses. And then move into new research that'll focus on integrating diagnostic with control capabilities in those commercially available offerings, and how we're looking to expand analytics through new data sources that'll pull us into the more earlier stage R&D spectrum. So it'll involve engineering-based approaches, as well as some deep reinforcement learning techniques that we're bringing to bear on these building-specific problems. Today's state of the art we call energy management and information systems. Effectively, these technologies are bringing in data across a diversity of sources, whether it's smart meters, whether it's on-site distributed energy resources, data out of building automation or control systems, et cetera. And then across this broad family of technologies, providing diverse capabilities in terms of interval meter data hourly interval meter analytics, or sub-hourly, fault diagnostics, consistently analyzing control system data to identify problems and opportunities in an automated fashion, as well as advanced predictive HVAC system optimization. This is all being delivered to market in commercially available software tools. Here's a couple of examples Starting at the top left and going clockwise, an image from a fault diagnostics tool used very pervasively across, especially UC campuses. Every line on the screen represents some problem being monitored with some piece of equipment, and whether it's presently manifesting or not, so that operators can take action to resolve the issues. Moving clockwise then are a screen grab of predictive HVAC optimization software, typically providing something like day ahead, optimal supervisory control back to the building, often decisions made in the cloud. And in the bottom, energy information systems are analyzing that hourly or sub-hourly meter data to give us load profiles to understand how much energy is being used at what times of day at different points in the building, whether that's whole building, whether it's specific floors or specific systems and pieces of equipment. These are very much human in the loop technologies. Once results from analytics or visualizations are presented to a user, there's a need to take action and make improvements based on that information. The technology then provides a convenient location with under the hood capabilities to continuously track improvements and measure savings. And that's just a continuous virtuous cycle that's happening there. Before we conducted the study to generate the results I'll share with you, the state of knowledge was that there was big savings potential, 5 to 15%. There was a growing body of case studies highlighting that potential. They were often conducted by product vendors. They were using diverse methods and metrics, and you couldn't really synthesize those findings to generalize how much the technology saves. Unlike hardware, there was no information and remains no information in the public domain around what does the software analytics cost. You cannot find that. It simply is not available. The result was that the technologies were under, and still are, under adopted because there was a lot of uncertainty in the business case and the value proposition around what you might get from implementing these systems. To address some of these barriers, we conducted a 4-year study, worked with 104 organizations who were implementing analytics in a broad install base. We wanted to provide them technical assistance to maximize the savings they could achieve, and through working with them, collect enough information that we could provide broad evidence base on what is that value proposition. So we worked with 500 million square feet of install space across these partners, and some of the high level by the numbers. Meter analytics users saved on average 3% whole building. Fault diagnostics, median savings 9%, all with very rapid payback, two-year payback time period from the median user. And this represented some 40 different commercially available technologies across this cohort of analytics users. There was, on the bar chart on the left, pretty good representation across different building types. A lot of office, higher ed, healthcare and lab, and then some onesies on the other sectors and verticals in the commercial space. Most of the organizations, these are large portfolios, they're enterprise organizations or campuses and universities, so that most falling in the 1 to 5 million square feet bin for their portfolios. That's in the middle chart. As far as technology types, about 1/3 of the participants in this work were using exclusively those hourly or sub-hourly meter analytics. The rest were using a combination of fault diagnostics and the energy information systems. Benefits. What was really interesting about this finding was, of course, energy and utility cost savings. But we also saw the power of the data in these tools that could be used to either validate project level capital projects and the savings that are being created through those investments, or to inform those capital retrofit strategies. And there's additional non-energy benefits around improved occupant comfort and O&M, operations and maintenance staff labor savings from streamlining their processes through these automated tools. How are the savings generated? This was critical to understand, like specifically what are users finding with these technologies? There's really a lot around scheduling. So making sure that systems are shutting down when they're supposed to, that lockouts from, say, maintenance interventions are not continuing in their unreleased state. A variety of measures all around reset strategies, whether that's duct static pressure, supply air temperature, or at the chilled water and hot water reset points at the central plant level. And then there's also a class of savings all around just ensuring that set points are appropriate and not overly aggressive for the needs of the spaces being conditioned. Cost is a huge contribution of this study. As I mentioned, you can't find this information anywhere in the public domain. We broke costs into upfront one-time install and configuration, and then ongoing costs hi Josh. There's your rock star participant from UC Davis campus in this study. You all have a terrific team there, very much at the leading edge of what the nation's energy management teams are delivering to their buildings and occupants. I'm glad you're here. So recurring costs, annual software licensing, services around commissioning, complementary services from the software providers or others to help the implementing organization make best use of the technology. These costs are for very large portfolios. They don't necessarily translate into like what you might expect for a single building install. We could look at the cost per data point monitored, the cost per building monitored, or the cost per square foot. And a couple comments I'll make. There's a lot less data that's being fed into the meter analytics tools. And a lot more data being ingested by the fault diagnostics tools that are looking at all the control system data. Orders of magnitude differences in the number of points being analyzed, integrated, and maintained. You see that reflected in the per point and per building costs between that top row of meter analytics EIS and the bottom rows on fault diagnostics. At the end of the day, across these large portfolios, those ongoing costs, either a penny a square foot median or 2 cents a square foot median. So by then things kind of normalize out. Remember that these costs are rapidly recouped with a median payback of about 2 years. And that's driven again by either 3% portfolio-wide savings on the meter analytics, energy information systems, or 9% on fault diagnostics. I want to emphasize how significant that is when you think about one-off component level measures, even if it's comprehensive, say, variable frequency drive upgrades or lighting, which most commonly are getting you more in that like couple to 5% range. So 9% whole building savings is remarkable and significant. Product trends. I think we'll see some convergence between the interval or smart meter analytics capabilities and the fault diagnostic capabilities within single offerings. You can find examples of that in the market now, but it's not as common. And I think as time goes forward, we'll see more unification there. Summative views or views into the findings that provide users some level of prioritization is really critical for these technologies. You imagine you have many, many buildings in your portfolio and you're generating insights into all kinds of operational issues. So how do you triage, how do you prioritize what you're going to do, you know, first, second, third, this week, this month, this year? And some providers offer support there, some don't. The marketplace is thriving. There's you know, over 100 offerings out there just that my team is aware of, and more constantly. The predictive HVAC optimization is much more emerging and more, there's fewer offerings there. We understand a lot less about how well those technologies perform under what conditions, and I think that's a good area for continued research. Machine learning is something everybody wants to know about. We're all intrigued to how we can use it to better solve our problems in building energy efficiency and operations. It's barely coming into product, mostly around areas of data tagging and point labeling, predicting load, and it's used in some of those very few control optimization technologies that we see available. So these results are from this study are available. The website is listed at the top of this slide. There's a report that gives all the technical details that's complemented with an applications showcase that highlights all the best practices across that cohort that we engaged, and a kind of one sheet value proposition business case summary that goes along with it. That's really an owner audience. So I hope I've given you a good grounding in the state of the technology and really what's happening in actual buildings with product that can be procured and installed today. And I'm going to talk now and shift my attention to two ways in which we're looking to advance the state of the art, starting with automated fault correction. So the fault diagnostics tools that I talked about ingest data from control systems one way. They're pulling data, they're analyzing data, and they are presenting findings to a user. In this effort, we're looking to close the loop and actually open a two-way interface with the control system, implement corrective action on a class of faults that can indeed be corrected through controls and software. So that's all the things related to control and scheduling. We can't fix leaky valves or stuck dampers, obviously, without an actual wrench turn in the field. But this is what we're looking to do in this project. We have a few steps: developing a library of automated fault correction routines. That's the engineering logic to take corrective action once a controls related fault is identified. We're working with partners who provide FDD product to the market for them to integrate these routines into their commercial product offerings, and then field testing and documenting the findings on, does it work? Have we screwed anything up in trying to correct problems in the field? We're delighted to work with some of the nation's largest FDD providers in this project on the implementation side, as well as a broad cross-section of advisory partners who provide an immediate audience for the results. Here are some of the correction routines that we're working with across that set of partners. They're categorized into things that are like hard faults versus those that represent more opportunities to improve further. So you will see, problems with biased sensors, incorrectly programmed schedules, rogue zones that are driving system operation to the extreme. Opportunities are all around reset strategies, lockout set points on economizers, and zone temperature set points, and ensuring that those are appropriately set and set back. This is just a schematic on what that process really looks like in a sort of coded environment. What happens, the FDD tool finds a problem, raises a flag, that then triggers the correction routine to execute. And really what that means is you're overwriting specific parameters in the building control system to make those changes. So you're taking the old value, the logic is telling us what the new value should be, and you're writing that back over the control system network. Establishing those two-way communications was a really non-trivial lift for our partners. They have to kind of re-architect the systems that they're working with. Here's examples from 2 of our cloud-based FDD partner offerings. There was one on-premise solution. That was much easier. Effectively, the red lines are showing the new communication paths that need to be established from the cloud across the firewall to the on-site appliance or data acquisition device and back onto that control system network. One partner did this kind of in an all-in-one bundled fashion. Another basically installed a brand new execution hardware device on site to accomplish this. The point being that this does require system architecture upgrades. Operator acceptance is critical. Operators are quite rightfully reluctant to just let a diagnostic system take control of that's not done. This is very new and pushing the envelope work. So our partners figured out how to update their interfaces to allow an operator to say, yes, do the auto correction, to hit the stop button, abort, this is not working, and to understand what changes have been implemented over time. I'll show a couple of just a couple brief examples from some of our testing sites. We've been slowed down from pandemic. It's really impressive that our partners have actually been able, nonetheless, to get into some buildings, 2 out of 3 of them so far, and actually execute some of these routines. We have a diversity of control system integration types. And I'm showing you some of the details around the buildings that we're working with. The first example I'll give is the correction of zone temperature set points. And, admittedly, so this system is basically, we have to, in the test routine, we have to impose the fault, which is some set point that we don't want to be active, and then trigger the correction routine, make sure that it held, that it did what it was supposed to, and didn't cause any unexpected, unintended consequences or ripple effects that would be problematic. So the set point, and this is a heating set point, is shown in orange. The blue line is the actual zone temperature. So in the start of the day, we have that heating set point at 21 C. That's not what we want to see. We go in and correct it back to a more appropriate 19 degrees. And I'm sorry, I think it's actually the reverse. We want it to be 21, it was at 19. And you can see the zone temperature responding as well with those changes that we've implemented. So here's a way for us just to draw data from the field, monitor what's happening, and prove that the system is behaving in the way that we intended. The next example I'll share is improving the supply air pressure set point reset in the air handling units that we were testing on. So the first thing I'll draw your attention to is the bottom portion where we're showing this kind of heat map plot. And what you can see is across these different rooms or zones, there's one zone that we call rogue. It's damper command is blown open, it's 100%, it's not modulating. And that is reflected in the plot above, where we're showing what the set points are and what the actual recorded values are in the control system. As soon as we implement our corrective routine, now if you focus your attention on the top plot there, you can actually see that instead of being pinned to that old value, that red line, we actually see now some modulation in the system. So we have indeed moved past the rogue zone, driving everything, and we've regained better control of the system here. Our early results, I'll say, have been encouraging. These initial tests are documented in an article in Energies. I'm showing you here on the slide. A lot more detail around the rogue zone detection, the supply air temperature set point reset. We have ongoing testing across all of our partners. We just had a meeting yesterday of the technical advisory group for this project, and always some really terrific details around how things are being implemented, all of the nuance around across different systems. What does it really take to get this stuff to work? We'll be, over time, looking to assess how the full complement of 10 routines actually works in the field, documenting all of the labor, like what does it really take to implement this stuff? Like how many hours to establish that two-way BAS connection? How many additional points did we need to surface through the control system that were never even otherwise available? Really to inform further uptake and expanded integration of these solutions by others outside of our first set of implementation partners. So I'll say, you know, what's important about that work is integrating and better connecting the diagnostic side of the equation with the control side of the equation. Hopefully providing techniques that will reduce the residence time that some of these controls related faults are present in the system. If you can auto correct it instead of calling a controls programmer or sending, you know, someone, some human to intervene. And doing that additionally, this is, it's not like a brand new concept, but doing it with partners who offer commercial product to the market is also a critical contribution, because there's a lot of stuff that we can cook up in our R&D, in our living laboratories at our campuses, in code that we architect as, or I should, architect is too strong of a word, code that we craft as researchers, and moving it into real product environments is a key step, and something that's really exciting to me about this work is that we have those partners right there with us on that journey, and a quicker path to market and impact. So that was using engineering logic and expertise to advance the state of the art by integrating diagnostic and control. The last thing that I'll introduce in today's talk is around expanding analytics through the use of novel data sources. The kind of backdrop here in terms of opportunity is driven by more recent advances in the availability of public data. So we have, more information available through energy disclosures, through open access to permit data. We've got advances in sensor technology and associated falling costs. And this is all coming together to bring us an increased number of data collectors that we can access for the work we want to do in buildings. These new data collectors, combined with feature extraction techniques from machine learning and computer vision, then together hold promise for us to improve our capabilities to identify building characteristics, building assets, like physically speaking, and to identify efficiency measures at the building specific level. So here's a little bit more on the types of data that we mean. Over here in the red, meter data, weather data, that's the bread and butter of all the existing technologies and the work I showed you in the first portion of the talk. Kind of going counterclockwise, there's the public data sources, and really what I'm going to talk about in this portion of the talk is work that focuses more on those light gray squares, RGB and thermal images, street view and aerial and satellite images, even LiDAR in some cases where that's available to us. We can look to fuse all of this data using, all of our image processing, machine learning, natural language processing, and through that pull out new information on those characteristics and efficiency opportunities that we're so interested in identifying. So I'm going to talk mostly about, not mostly, about drone-based thermal and RGB images. So costs of cameras and drones have come down incredibly recently, making it like we can get really, really sophisticated stuff within at price points that our R&D budgets can bear. That's really exciting. A lot of work in photogrammetry software, machine learning, computer vision, et cetera. And this is what we're taking advantage of to apply to do things like auto-generate 3D geometry. I'm going to show you that. Extract features from the exterior of the building. That might be packaged rooftop units, rooftop photovoltaics. I'm going to show you how we're detecting windows and window to wall ratio, and also identify thermal anomalies. So I'll start with generation of 3D geometry. This is using RGB images. The very first thing we do is find a building of interest and do our flight plan. We have to figure out how we're going to run concentric flight circles over the building of interest and how we're going to position the drone to get a good set of images out of our RGB cameras. This is going to give us a collection of 2D imagery like you see in the right-hand corner of the slide. From there, we post-process the images using already available photogrammetry software. And this gives us a 3D point cloud-based representation of the building. Point cloud, like closest analogy I have is if you've ever seen like the 2D pointillism art, where you get a whole 2D cool image just from like points and how close and far they are together. This is sort of like the 3D version of that. There's a lot of information as well as metadata packed into these representations. From there, we apply from computer vision, Huff transformation and polygonization to extract the building footprint and estimated building heights. Once we have that, we can then create that building 3D model in a GeoJSON format, which makes this 3D representation conveniently available as inputs to other analytics software tools. Now, what was fun about this is like, okay, you can do it, but is it practical? It's about 2 hours to acquire the images and do that flight over a medium-sized building. About, depending on your computer, about a day to post-process that data using the photogrammetry and generate that 3D model. This is all documented in the SPIE paper from Geospatial Informatics. That's pretty exciting when you think about the capability that in a couple of days of labor time, being able to create 3D representations across something like perhaps a portion of a university campus. So that's one way that we're using images and drones as data collectors. I'll share how we're looking at window to wall ratio estimation. So that's a really important building characteristic or parameter that we use in simulation modeling. There's a lot of tools that will allow you to input some information about your building. They have simulation instead of data-driven analytics under the hood, and they'll give you a list of recommended measures. So as a concept demonstrator, we're saying, okay, it would be useful to really perhaps know the actual window to wall ratio instead of some estimate or some defaulted value. So the way we do this, we start with a deep learning semantic segmentation model from the literature that is given in the bottom of this red boxed portion of the slide here. This is a Deep Lab V3 Plus for anyone who's been looking at this space. We pull a whole collection of images. We scrape them basically from every source possible on the internet, apply augmentation algorithms to flip them, to rotate them, to change the contrast, and to artificially increase the size of our training data set. We then have to hand label those images for training and say which pixels are actually windows. From there, we can take this existing deep reinforcement learning architecture from the literature, train it, and tune the hyperparameters appropriate to the tasks that we want to do, which is identify windows in our RGB images. The output there, those predicted window masks, are those kind of binary representation of where the windows are. That corresponds, if you can see my mouse where I'm moving it, that's kind of this row of windows and this front row of windows that have been pulled out in the mask. So next, we then have to bring in the third dimension. So we pull back in our 3D building model and we project the facade corners from the 3D model onto the RGB images. We pull in some of the metadata from those photogrammetry point clouds, and that allows us to associate each 2D pixel with each 3D pixel. Next, starting on the bottom right, we take the window mask, we take the knowledge of which points correspond to the facade corners, and then we're able to detect the windows on each, not just the the pixels on the 2D image, but on each facade. So we've brought in that Z dimension to the problem. Following that, a Delaunay triangulation allows us to position the window points relative to the facade corners. We can then project back onto the 3D representation. That gives us all the geometry that we need to compute the window to wall ratio for this building. Easy, right? No. Next, I'll show you the third application, thermal imaging and thermal anomaly detection. So this is compelling for us because none of the existing technologies that are available today are really able to gain much insight into the thermal performance or aspects of envelope. We're pretty much working with smart meter data, weather data, control system points, whether valves are open or closed. So this presents huge opportunity to bring in a missing piece of the puzzle when we want to identify improvement opportunities for the buildings. So in this case, starting on the upper left, now we're bringing in our thermal camera. So we've got a drone fitted out with an RGB camera and a thermal camera. The same thing, we're going to fly those concentric circles over the building of interest, but in this case, they have to be tighter. So you can't get a, if your loops are tighter, you're making more circles for the thermal imaging. We're pulling out those 2D, RGB, and thermal images that we've captured and doing 3D reconstruction with that off-the-shelf photogrammetry software. We're doing that on the 2D and on the thermal, the RGB and the thermal. The thermal is in that more grayscale on the right there. Again, we pull out our 3D building model. And now what? So again, starting on the bottom right, we're again doing our 3D, 2D matching. So we're projecting the 3D model onto the 2D thermal image, pulling out which pixels are only the building. We don't care about the parking lot and all the things that are to the side of the building, just focus on the building. And then we're going to, from this thermal representation, apply a k-means clustering, some additional morphological operations, and use that to extract the contours, that's those red shapes, of the detected anomalies from our images. And then we can superpose them back onto the 3D and show an analytics software user where the anomalous regions are. And there's ongoing work to quantify how problematic these anomalies may be and take us one step farther to actually identifying improvement measures as opposed to just the fact that it's leaky around our windows. Additional work. So I give a link here to some additional work that I haven't presented today, but that's basically pulling out building footprints from satellite and aerial images, techniques to fuse those with LiDAR to create 3D geometries without drones. Second, and some of that's the GitHub link that I'm giving here. Excuse me. Field testing, we're putting these methods in the hands of efficiency project implementers to understand. It's like, okay, we're doing cool stuff, we're providing new information, but is it actually valuable in creating additional insights into efficiency opportunities? Along the way, we're always looking to release the code that we create as well as the training data sets. Folks who've worked in some of these deep learning applications know that you can only, there's a lot of effort required to put together the training data for your specific application. So through doing that, we hope to enable adoption as well as further extension of some of the solutions that we're coming up with. So through what I've shown so far, I'm hoping to kind of take you guys through an understanding of what's happening in today's buildings, some fun work that we're doing to try to extend the state of the art and improve the analytics that we can provide to building owners and operators. And I want to, I'll just wrap up with some concluding remarks. First If anything, I want folks to take away the understanding that remote analytics technologies are available and enabling cost-effective deep savings today. Second, that new sources of data, the state of the art in feature extraction and fusion techniques give us a lot of promise to further advance technology capabilities. And third, I grounded everything today in thinking about efficiency measure identification, but there's a lot of other applications that we could envision, whether it's general outdoor asset identification, citing and tracking distributed energy resources. There could be sort of urban design applications around planning the hardscape, or something that's of key interest in the efficiency community today, being able to inventory more localized building typologies so that we can go a layer deeper in our understanding of the stock and better plan and target the delivery of programs for deep and material energy reductions across our stock. Concluding comments on lab research. I have been incredibly happy at a national laboratory and Berkeley lab in particular. This is a really rewarding career option for folks. Immediate opportunity for real impact of the work you do. You can undertake research that spans anywhere across the very basic to highly applied spectrum of activities. We're always recruiting, we're often hiring. I would encourage anyone in attendance to please contact me if you are interested to know more about what do national labs in general have to offer and what does Berkeley Lab in particular have to offer. I want to thank you for your attention and for hosting me today. And that concludes my seminar.
All right. Dr. Granderson, thank you so much. I see the applause signs on the Zoom and lots of snaps happening. So that's our Zoom version of an applause. So thank you so much. And now we have some time for questions. What I ask people to do is to either put it in the chat line or to raise your hands, and I'll try to just let people ask their questions in the order in which we see their hands raised. I see there's already a question in the chat that came in from Greg just now. And Greg, shall I read it out, or you can just chime in right away, either one? I'll read it out then. Greg asks, you mentioned that some of your research involves market research intelligence, which I traditionally think of as research in the realm of business and corporations. What is the role that labs and other academic institutions should play in market research? Please.
Yeah, thank you. Great question. It's really one of the reasons we need to do this. And maybe don't read too much into the word market intelligence. But I think it's appropriate. But if we want to provide innovation and R&D that will advance the capabilities of what's currently available, then we need to know what's currently available. We need to really know a lot about what are the techniques and methods that are actually being employed in these technologies. And let me tell you, there's a lot of really fascinating work that's happening internal to these companies. Everyone, now 5, 6 years ago, 7 years ago, not every analytics provider had a data scientist on board necessarily. Today they do. So that's one reason why we really need to stay abreast of what's out there and what's available. Second reason is that one of our roles, if you think across that, like research, development, demonstration, and deployment, is to provide information to building owners and operators about how they can best make use of the latest and greatest technologies in their buildings. So we need to intimately understand what's available, what can it do, what can it not do, what's marketing and advertising and hype versus a real capability, so that we can work with folks to derive the maximum benefit that they are able. So that's a big role for labs across federal programs, is to provide technical assistance. I hope I answered your question there.
Dan, please go ahead with your question.
Hi, thank you so much for being here. Great presentation. So my question was sort of early in your presentation, you had a study about the adoption of analytics tools, and you had it broken down across sort of building types. And I was wondering if you've seen a specific trend in the adoption in public versus private sector, and what your sort of feeling of the response is to adapting these technologies with policy and decision makers in the public sector versus the private sector.
Thank you for the question. The public sector has traditionally led the private sector. I think it's fair to say a bit in as far as adoption of analytics in commercial buildings. That's I think in our actual cohort of participants, I think we were split pretty even across the board. And I think that, it's really hard to know, like, market wide who has this in their buildings and who doesn't. I think with the 105 organizations that we worked with, we got a pretty good cross section. And you saw a lot of the, like, office and lab kind of represented there as also, I think, where we tend to see a lot of uptake. There was a third sector, I'd have to rewind to see that. So then I think the second part of your question was around policy making and adoption. So one benefit of the work that I really want to emphasize is that we're showing the value proposition. It's like, if the findings are not just for owners and operators, but we certainly hope that there are policy decisions now that we think we've pretty much closed the book now and said, okay, even though it's squishy, even though savings vary, we're establishing a very broad evidence base for what the benefit can be. And it's really my hope that that will spark more adoption through broader scale deployment channels. That might be ratepayer funded programs. That might be municipal level ordinance. That could be voluntary or mandatory codes, and making sure that we have the right infrastructure in place. Or it can be some of the like regional efficiency organizations and some of their market transformation activities.
All right. Michael Huang, if you would like to unmute and ask your question, please go ahead.
Hi, Jessica. This is Michael Huang from Stanford University. I just wanted to learn a little more about how the two-way FTD handles rogue zones. Does it just automatically exclude it, like a technician would go in there and just essentially delete it, or is it smarter than that?
Great question. It's as if you were in attendance in our advisory group meeting yesterday. So so in this particular implementation, basically the requests from the rogue zone are being discounted or not factored into the decision. And so a question actually came up, well, hey, do you always want to throw it out? Like, it may be rogue, but maybe it needs what it's really calling for. And basically the team implementing that routine, I think, have carefully bound it based on what they're seeing in their building zones and systems. And I think there is like a 12-hour or some time cycle on which, you know, it's never just like completely discarded. It's obviously still there.
Got it.
But I think, so your question is great, actually, in surfacing a lot of the very technical weeds and nuance around how it is that we want to go about addressing these problems. That's whether you have autocorrection or not. Yeah, I'll stop there. Thank you for your question.
Thank you.
So we've had a bunch of questions line up in the chat here. So I think the next one in line here is Subrijit. Is there energy savings potential by using the same technologies or methods in residential buildings?
Yeah, so yeah, thank you for bringing residential buildings into the conversation here. So all of my work is in commercial buildings. I think with the systems, so I guess let me start by saying the same methods, yeah, probably in the sense of, you know, the methods that we use for acquiring data, the methods that we use to generally analyze data. The systems and equipment are much different. Homeowners and what they want to happen is much different. And the world of fault, so I'm speaking just like very generally there, the world of fault detection specifically for residential HVAC systems is a totally different nut. You're talking a lot about either, I don't know which side of the coin you're on, problems or opportunities that might be associated with installation that a homeowner may never ever be aware of. Your user could more be on the technician side. So there's a lot, it's a very different situation on the residential space there, where I think there could be good cross information is around aspects of technology and associated business delivery models, what services are being provided, who's asking for them, where is the benefit coming into play. That's where we've seen a lot of innovation in commercial building fault diagnostics more recently, and expansion in business models and service models. And I think the same opportunities could potentially move the needle in the residential space. And I'm going to stop there because it's not my field of expertise and I don't want to get ahead of myself.
Thank you.
All right. I don't see any hands raised. So the next question here, I should add that a lot of the chat is thanks for the great presentation. So the next comment here is, question is, do you collaborate with Joshua New at LBNL on any of the building shell synthesis work? If yes, have you compared the accuracy increase you get from the drone data versus just using street view and satellite data for at least the wall to window ratio?
I know Josh New, I'm a big fan of his work. I was talking to him just earlier this week, actually, in a multi-laboratory confab on things we're all doing collectively in fault diagnostics. Yeah, he's done a lot of work in this area as well. It's probably worth us rechecking in on the actual level of results, because we now have those. And I don't know that we're going to be able to do a one-to-one like comparison of accuracy, but it's you're noting a really strong connection point with some of our colleagues in the lab complex, and Josh is great. I also need to check in with him on auto-tune and how that's all going.
All right, some more questions from the chat, I guess. Also, to students in the seminar, to egg students in the seminar, Ali just posted a reminder that if you want to join the lunch discussion, please get in touch with her so she can share the invite. So this comes from Craig Bender. I don't see the value of a window to wall ratio without knowing whether the window is single pane versus double pane or triple pane, for example.
Mm-hmm. Yeah, so First, I think like people using these tools are probably more likely to know whether they have single, double, or triple pane than they may like the window to wall ratio for their building, at least without digging deep into documentation. So it's not to say that this as one item of information is going to be world changing. Oh, now that I know window to wall ratio, I know what to do with this building. Not at all. This is mostly a first step in demonstrating new methods to understand valuable features and characteristics of buildings. So we're trying to see, can we make it work for window to wall ratio? That's something that we sometimes have to estimate. My next question of myself in this work is going to be, how much does it really matter versus some default value? More generally, I think it's useful to know at what level can we reliably extract information on these features, right? So there's window to wall ratio, there's whether there's balconies, whether there's rooftop PV or packaged units, like, and then like, what are we gonna do with it? And how does that help? So I mentioned in some of my next steps, really wanting to work with those boots on the ground implementers to understand what is the value of this enhanced information. Does it change our answer at the end of the day? If it doesn't change the answer with or without it, then let's look at other applications where we can create more benefit. So I hope I answered your question there. I mean, I think I agree with you that without other things, window to wall is not going to do as much.
All right, we have some more questions showing up in here. The next one, though, this comes from Carlos Santa Maria, and I have to admit, I'm not sure what the full question is. So please, unmute yourself if you'd like to ask it. Go right ahead.
Yeah, sure. Hi, Jessica. Good
Hi,
to see you
Carlos.
again. I have a question. As a lot of these technologies and solutions mature and they're out there, we've seen over the years that the implementation, while it's not as much as we would like to see it, the technicians or the building engineers out there are becoming less and less trained into utilizing them and making them effective. And, over the last, during COVID, the last 7-8 months, I've been in probably 30-40 buildings conducting evaluations. And I can count on one hand the amount of buildings that really had a fault detection or a data analytics, real-time energy dashboard of some type. And for that matter, utilizing it or understanding it to where the data is relevant. So, working with the community colleges, we're trying to figure out a good program to slowly get students into adopting and being familiar with the data analytics part of energy management. So it's more of a question on how you see or what is effective out there with some of the baseline training that others may be conducting out there.
Mm-hmm. Workforce, I think for, technicians at large is a big issue. So can people make use of technology? I think it's getting better over time. I mean, Carlos, I hope you would agree that from, what you may have been dealing with 10 years ago, that things have gotten a little bit better in terms of providing insight as opposed to just a slew of data, maybe even 15 years back at this point. Generally speaking, though, I think that's always been an issue with or without analytics. Do we have the right know-how to keep stuff running, to keep it running well, to find problems and fix problems? Maybe it's like too rosy, but one thing I'm hoping is that access to more modern data-driven tools that provide enhanced insights and analytics is hopefully somewhat more aligned with the expectations of a younger workforce, and that can also be some draw to continue the pipeline where You know, I'm not going to put you in front of exclusively and only in front of a 1990s vintage funky control dashboard, but we actually have modern tools available to us in this industry as well. This is not, we're not back in the dark ages in building operations. So I don't think I really, you know, answered your question head on, but that was just a little stream of conscious flow from me around workforce.
Yeah, well, thanks. I just think our technicians, and even having, you know, the sophisticated energy management systems, the medicines out there that do have the capability of fault detection, we're still at the same place we are 5 years ago with adoption and implementation. These are great conversations, but at the same time, we have a workforce that isn't being educated on the capabilities of them to more comfortably understand and utilize them. So
I
think we're all
definitely
saying the same
agree.
thing.
Yeah, I would take a little bit exception to with adoption, the same place we were 5 years ago, because I do think that we're seeing a real uptick there. From my perspective, just, you know, like kind of across the country, but it's definitely not where it should be and where it could be.
Okay, thanks.
It's all relative, right? We're improving
Yeah.
over a previously very small number.
So we don't have much time. We have 4 minutes left. And I guess maybe based on how that conversation, that question ended right then, maybe I'll skip to the last question that came in, which was about, which is from Kevin Smith. And he says, as an instructor of HVAC technologies, how would a student acquire information on introduction to deep learning technologies?
Kevin, I haven't been in the school for a while. You're asking a great question. So how would we acquire information in intro to deep learning? So I think are such, I guess I'll kind of turn it back. Like, are there intro to machine learning? I think we're seeing those. I think what we don't have that we probably need a lot more of is that was much of the work here, and why it's appropriate for national lab researchers to be working on. The stuff that comes out of the computer science domain is not immediately applicable to our problems. There is a huge lift in when I presented and I said, oh, so we scraped data and we tuned the hyperparameters. Okay, that was PhD level statistician working overtime to learn the ins and outs of the latest and greatest in segmentation and how to go forward doing that, not to mention the computational power that's needed. I don't have the answer to the question. I appreciate the question. It's highly relevant. So maybe what that says to us is that we have opportunity and need on the academic side to join forces across divisions and departments and bootstrap some learning around what it really takes to implement a lot of these algorithms.